Welcome to our fourth electrochemistry video. We're getting there. We're going to do a lot of practice problems in this video involving a new equation, but first we're going to talk about line notation. It's another way to basically explain what's going on inside of a cell. So here, if you we have two different situations. Here's situation 1 and here's situation 2. So this whole line up here in situation 1 all the way down to copper solid, they all go together. I'm going to not draw that line. Okay, so here we have zinc solid and then a single vertical line, zinc 2 plus aqueous 1 molarity, sulfate 1 molarity. So a single vertical line, like this one, indicates a phase change from solid zinc anode to aqueous zinc sulfate solution in the anode compartment. So this whole section here, I'm going to underline in green, is describing a compartment that has a solid zinc strip like this. So there it is. And it's saying, oh, it's going to change phases from that into aqueous zinc sulfate 2 plus solution. So you can have like a little water line or whatever. Okay, so that single vertical line represents a phase change. The double vertical line represents the salt bridge. They're saying this is where the salt bridge happens. So I could draw a salt bridge like this that connects my two different compartments or buckets, beakers, whatever. So here's my next one. So I'm moving on to the next one now, and it's saying there is copper 2 plus aqueous 1 molarity and sulfate. Okay, vertical line, that means phase change. It changes into a solid strip of copper. So it's saying it starts off aqueous, and then here's my strip of copper. It becomes solid copper. So this is written in the order of the change, I guess you could say, like zinc solid turns into aqueous zinc. And in this situation, aqueous copper turns into solid copper. So they're describing your cell. Another way it could be written, it's a little bit simpler. They just leave out the ions because they really don't contribute to the cell. So they show, okay, zinc solid is turning into aqueous zinc, salt bridge. Copper aqueous is turning into copper solid. So quick review, if zinc is turning into an ion of zinc, what is that, a cation, is it being oxidized or reduced? It is being oxidized because it lost electrons, which means this one must be being reduced. And if it's being oxidized, that means it is being, is it an anode or is it a cathode? It's an anode, and I like to remember it as red cat, reduction cathode, and then you can just say, oh, the other one's the anode. So that's line notation. You want to be able to read it. Okay, so Gibbs free energy and redox reactions. Quick review. We know that if the E is positive, that is spontaneous. However, if delta G is negative, that is spontaneous. Remember, they're opposites. Negative E, non-spontaneous. Here's a couple or a few equations. We already know this one. N in this unit is representing number of electrons transferred. Number of electrons transferred. We'll practice figuring that out in the next few problems. F, we already used earlier, is Faraday's constant. We use it to convert from coulombs to moles of electrons. It's just a constant. And E, of course, represents EMF, electromotive force, represented by volts or joules per coulomb. And if your delta G is standard, then you'll come out with a standard E. If it is not standard, neither will be standard. So these are handy little equations. So here is something that will allow us to practice. Find the standard Gibbs free energy and the equilibrium constant, K, for the following reaction at 25 degrees Celsius. Is the reaction spontaneous, and which way does equilibrium lie? So there is our reaction. It's manganese and chromium. So what's really good to do first is lay out our equations. So all I'm given is the equation for the reaction, and you can assume that you are also supplied with a chart of standard cell potentials. So if I wanted to, I could look up the reduction potential of each of these if I wanted. I just learned a new equation. It is right here. Delta G standard is equal to negative n Faraday's constant times the standard E. So let's see, I want to find delta G. Can I figure out how many electrons are being transferred within this equation? Yep, that's something we can figure out. Faraday's constant is a constant. Okay. Standard cell potential, can we figure that out? As long as I'm given these values? Yes, I can. We can figure that out. So this is how we're going to find delta G. So our first step is to figure out our reduction potentials. So these are not given on that standard small little chart that was in your notes. You'd have to go to the internet to find them, and I have done that for you. So for manganese, it's negative 1.18, and for chromium, it's negative 0.74. Okay, well, from the previous notes, we know that the E of the cell is equal to what minus what? Is it anode minus cathode or cathode minus anode? It is the E of the cathode minus, and standard, E of the anode. So I need to take these numbers and find the difference. I need to know which one is the cathode and which one's the anode, though. So let's figure out what's being reduced. Reduction is gaining. Leo the lion says grrr. Gaining electrons is reduction. So what's gaining electrons? Manganese or chromium? Chromium is gaining electrons. So this right here is our cathode, which means this must be our anode. So I'm going to do negative 0.74, these are all in volts, minus a negative 1.18, and I come out with 0.44 volts. Okay, so now I have this number up here for my delta G. Let's start plugging those in. Delta G is equal to negative n, number of electrons transferred. So in this equation here, how many electrons are being transferred between chromium and manganese? Well, let's see, we could just look at one or the other. Let's look at chromium. Chromium goes from 3 plus to a charge of 0. So that means that each one gained 3 electrons, but there are 2 of them, so how many electrons got moved? 6. So negative 6 times Faraday's constant, 96,500. What are the units on that? Coulombs per moles of electrons, which is handy because that negative 6 is in moles of electrons. Okay, times my E, which I just got, is 0.44 volts. So I end up with a delta G of negative, it comes out as like 250,000. Well, that's in joules. And this is actually going to come out per mole. But I want joules per mole because that's really, really big. So I'm going to convert it. This comes out as negative 250 kilojoules per mole. Okay, awesome. There's my delta G. Standard. If you're wondering where that per mole came from, it's you could think of it as coming out of that E value. So now that we've got delta G, let's figure out K. Do we have an equation that involves K? Yes, we do. It's delta G is equal to negative RT natural log of K. So if I want to solve for K, I need to do delta G over negative RT is equal to the natural log of K. And you might remember from, I think it was the kinetics unit, way back when, if we want to get rid of natural logs, what do I have to do? I have to do e to the, and that cancels this out. So I know that K is going to be equal to my delta G, so I'll plug that in now, negative 250 kilojoules. You know what? My R value that I use for these is 8.314 joules per mole Kelvin. So should I be using kilojoules in this equation? Probably not. Joules. This is per mole over R, 8.314 joules per mole Kelvin, and then times my temperature. And that was, what is it? Should be in Kelvin, so 298. And whew, sorry for how tiny that is. You should end up with the K value that's shown at the bottom of the screen, 6.6 times 10 to the 43. Okay, so let's use our K value to figure out which way the equilibrium lies. Is my K value very... Ooh, I got a text message. Is my K value very, very large or very, very small? It's very, very large. Since it is so large, that must mean I have a lot of products. So it lies far to the right. Now, let's figure out if it's spontaneous. I need to look at my delta G for that. My delta G is negative, which means it is spontaneous. So negative delta G equals spontaneous. And large K means equilibrium lies far to the right, lots of products. Okay, moving right along. Equations again. We have a new equation, woo, and it's the Nernst equation. That's a fun word to say. Nernst. So we have the E, so the cell potential, not standard, is equal to the standard cell potential minus RT over NF. N is still moles of electrons transferred. F is still Faraday's constant, times the natural log of Q. Remember, Q has the same formula as K, which is products over reactants. It's just maybe it's not at equilibrium. If the temperature is equal to 298 Kelvin, then if you want, you can use this equation. It just requires a lot less plugging in of numbers. I believe you are given both of them on your formula sheet, but again, you should double check that. So, typo. Proceeds. So as the reaction proceeds, the concentration or partial pressures of reactants decreases, and the product's concentrations or partial pressures increases. So in other words, we use up our reactants and we make more products. Something that's really useful to remember is when the system has equilibrium, or when the battery or cell is dead, when it stops reacting, when it's over and done with, E, the one on the left, is equal to 0. We will use this later. Over time, the voltage decreases because you have less things that are able to react and send voltage across. Something to keep in mind, standard conditions in this unit does not just mean 1 atmosphere and 25 degrees Celsius. It also means 1 molarity. That's important. So you use this equation when you want to find the EMF under non-standard conditions. You can use it to determine the concentration of a reactant or product. So let's analyze this a little bit first, and then we'll actually do practice problems. So let's say you have this equation where copper reacts with silver to form copper and silver. And we've got the standard cell potential here. If the system is originally under standard conditions, so 1 molarity, 1 atmosphere, 298 Kelvin, then we add in more silver. If we add in more silver, now its concentration is greater than 1. Think about Le Chatelier's principle from the past. If I add in more silver, that upsets the equilibrium, and in order to fix it, which way will it shift? Towards the right to use up that excess. So the rate of the forward reaction will increase, and the voltage then will increase. Any movement in the forward direction increases voltage because that allows the electron flow, the current, to also increase. However, if we do the opposite, what if we were to remove some silver? Then the reaction goes, oh no, that's not good. I want more silver in order to be at equilibrium. So it shifts back. So the rate of the forward reaction will decrease because the reverse has increased instead, which means the voltage will decrease, which means the electron flow will decrease. So voltage is related to how quickly the forward reaction is moving. So again, just another practice. Here we have copper, silver, copper, silver. This time we're going to talk about the reactants. If it's originally under standard conditions and then we add, did I say talking about the reactants? We're going to talk about the products this time. So if I add copper, I'm adding more of this product. It goes, oh no, too much of that, I don't like it. And it goes the other way. So if it goes backwards, is the voltage going to increase or decrease? It'll decrease. The rate of the forward decreases, or you could say the rate of the reverse increases. And then another situation is, what if we added more copper? Oops, sorry. What if we removed copper? And if we remove that copper, then it goes, oh no, not enough copper ion. I need to make more. The forward reaction rate increases, and the voltage then increases as well, and the electron flow increases. So you want to be able to analyze these. You still need Le Chatelier's principle. In fact, last chapter is going to get used a lot in the next 3 example problems that we do. First, let's calculate the electromotive force when copper ion is 5 molarity and zinc is 0.05 molarity at 298 Kelvin. So in order to do this, you are going to need those standard reduction potentials, so I'll just give them to you. You'd have to look them up in a chart though. So the E reduction standard for each one of these is negative 0.76 volts, and this one is positive 0.34 volts. All right. Well, they've given us concentrations, they've given us temperature, and they've told us to solve for E. When you see that mixture of information, to you that should scream, Nernst. And since it's at 298 Kelvin, I get to use my kind of shortcut Nernst equation, which is E equals E standard minus 0.0592 volts. Ooh, that is a funky 9. Over the number of moles of electrons transferred times the log of Q. So let's just plug them in. E is equal to the E standard, which is anode minus cathode or cathode minus anode? E standard of the cell is cathode minus anode. So let's solve for this separately first. What is being reduced here? What's gaining electrons? Copper is being reduced. Zinc is being oxidized. So what is my cathode? Copper is my cathode. So 0.34 volts minus negative 0.76 volts gives me 1.1 volts. So here I'm going to plug in 1.1 volts for my standard cell potential minus, I get to use this nice little shortcut, 0.0592 volts because it's at 298 Kelvin, over the moles of electrons transferred. How many electrons are being transferred between zinc and copper? just 2 electrons. You can look at the charge. That's the fast way to do it. Just look at the charge, and if it has coefficients, then multiply the charge times the coefficient. So 2 moles of electrons multiplied times the log of Q. Remember, Q is the products over the reactants, and then the exponents are the coefficients. This doesn't have coefficients. No, so that makes it easy. So when I'm solving for Q or K, do I include solids in my equation? Absolutely not. No solids. No solids. And in these equations, if it has a charge, it's not a solid. If it doesn't have a charge, it's a solid. So I'm only going to include zinc and copper in this equation. So zinc's concentration is 0.050 molarity. That's my product over my reactant of 5.0 molarity. And if I plug this all in, I come out with 1.16 volts. Be careful if you use this like shortcut equation, because it's at 298 Kelvin, it becomes a log instead of a natural log. So be careful. All right, here is a weird one. A cell under standard conditions and functioning according to the equation below runs until zinc concentration is equal to 1.14 molarity. Okay, hold on. It runs until it reaches that concentration. So is the cell still going, or is it dead? The cell is dead. So what does that mean about E? What is E equal to if the cell is dead? It's equal to 0 volts. This is something you want to learn to recognize. Our goal is to figure out the concentration of our gold. Okay. So for this, there's a little trick you can use where you don't even have to use the Nernst equation. What you're going to do is say, all right, well, it was at standard conditions. So what was the concentration of each of them initially? Initially, my zinc was at 1 molarity, and my gold would have, well, gold started off here. Started off at 1 molarity. Remember, I'm using my reactants for this. Okay, so it started off at that. Now, as the reaction proceeds, we apparently built up more of that zinc 2 plus. So what I could say then is the change in zinc is 0.14 molarity. So I'd say, all right, well, if I had a change in 0.14 molarity zinc, I'm just going to do some stoichiometry and see what the change in gold was. So I know there are 2 moles of gold. Oop, that's a plus sign. For every 3 moles of zinc. And I'll find out, okay, well that must mean that 0.093 molarity gold was consumed in the production of this zinc. Okay. All right. Well, I know if my gold started at 1 molarity, I could just say, well, 1 molarity. I don't know why I added an extra 0 on there. It's fine though. Minus 0.093 molarity. That tells me that I must have 0.907 molarity gold once the cell has died, once it's used up all of its juice. There it is. Okay, last one. So calculating the concentration in voltaic cells. So you're going to have to do some finagling with that Nernst equation here. If the voltage of a zinc hydrogen cell is 0.45 volts at 25 degrees Celsius, 25 degrees Celsius, that means I can use this equation. When zinc is at 1 molarity and the pressure of hydrogen is 1 atmosphere, that's not a concentration. Be careful. For Q, I could use pressures or concentrations, but I cannot mix them. What is the concentration of hydrogen? All right, this has the answer on there already. Just ignore it. And here's my equation. So I'm going to look at what I've got. So I know the voltage is 0.45 volts. 0.45 volts. I can find my E standard because I have a chart full of standard cell potentials. I know that number. I can figure out how many electrons are being transferred. Let's just do that right now. How many electrons are transferred between the two of them? Zinc goes to zinc 2 plus, so it's got a charge of 2. So I could say 2 electrons, no coefficients, just 2. So N is equal to 2. And then my Q is going to be products over reactants. So let's just do that over here on the side. Q is equal to products over reactants. So it'll have the concentration of zinc up here and the concentration of hydrogen down here. But wait a second. There's a coefficient. What do I do with that coefficient? It goes right there. So yeah, that knowledge that you learned, that information you learned way back when, you still have to use it. So let's get our standard cell potential. I'll give you the numbers you need. So for zinc, it is, what is it, negative 0.76. Hydrogen, you should have memorized. You're probably going, what? No, there's no way I have that memorized. So this whole numbering system is based off of hydrogen being 0. So you don't even have to look that one up. It's centered around hydrogen, hydrogen 0. That makes your life easier. So now we have to figure out what's the anode and what's the cathode. So you try that without me. What is the cathode? If you said that hydrogen is the cathode, then you are correct. Hydrogen is the cathode because it is gaining electrons, which means it has been reduced. Red cat, reduction cathode. So that means for my standard cell potential, it'll be 0 minus a negative 0.76 volts, so it's 0.76. So let's plug these numbers in now. 0.45 is equal to 0.76 minus 0.0592 over N. We said that 2 electrons are being transferred, times the log of Q, which is my zinc concentration. I have that. Over my hydrogen concentration squared. What a mess. So let's move everything over to one side of the equation if we can. So I'm going to do 0.45 minus 0.76. Oops. 0.45 minus 0.76. And then I'm going to multiply that times 2 and divide by 0.0592. So once I've moved everything over to one side of the equation that I can, I'll end up with 10.47, let's do 3, is equal to the log of 1 over the concentration of, I'll just say x squared. That's easier to write. Okay, well, I want to solve for x. That's my goal, and log is in the way. So how do I get rid of a log? We use 10 to the. With natural log, we use e to the. With regular log, we use 10 to the because it's log base 10. So these guys go away. And you'll end up with 1 over x squared is equal to 10 10 to the 10.473. So if you rearrange that, you're going to end up with the concentration of hydrogen. Well, here, let's write it like this. X is equal to the concentration of hydrogen ions, which is equal to the square root of 3.365 times 10 to the negative 11, and that gives you your answer of 5.8 times 10 to the negative 6. And remember, it's a concentration, so don't you be forgetting that M. I'll be very disappointed in you if you do. I'd forgive you, of course, but don't forget it. Okay, so these are different ways that you can deal with the Nernst equation. You are going to want to practice this. If you don't practice it, even though it might make sense right now, you're not going to be able to figure it out on your own on the test. So please, please, please practice. Practice. Do it. Do it. See you later.